To get us into some of the scientific and other concerns, we have someone who should be familiar to most in this audience. He's been an outspoken spokesperson on the question of what's likely to happen if we don't get enough water in the lake. With that, let me introduce Dr. Kevin Perry. He's a professor in the Department of Atmospheric Sciences here at the University of Utah. He will frame the problem, the causes and consequences of a shrinking Great Salt Lake. Thank you for joining us, Doctor.
Wow, it's great to see so many people here who care about the future of Great Salt Lake and all of the residents that live along here. It's really difficult to contemplate life without Great Salt Lake. Yet, due to an unsustainable water diversion, drought, and climate change, we're forced to do just that. Great Salt Lake is arguably the most important ecological oasis in the western U.S. And the saline lake, its islands, and the surrounding wetlands support a biologically diverse ecosystem that serves as a critical stopover and staging area for an estimated 10 million migratory birds each year. In addition, the lake is a recreational retreat for boaters, swimmers, bird watchers, photographers, stargazers, artists, hikers, mountain bikers, bird watchers, mountain bikers, duck hunters, and campers. Great Salt Lake contributes substantially to our local economy and gives rise to our reputation for the greatest snow on Earth. The lake also holds great cultural significance to both the settlers who declared that this is the right place and the Ute, Shoshone, Goshute, and Paiute tribes who have called this region home for millennia. Whether Salt Lake City and other residents along the Wasatch Front realize it or not, our very existence is intertwined with the fate of our namesake. To contemplate the future of Great Salt Lake, we need to first understand its origin. During the last ice age, which peaked about 18,000 years ago, temperatures in our region were as much as 5 degrees Celsius or 9 degrees Fahrenheit colder than they are today. And paleoscientists have used a wide variety of proxies and computer modeling to establish that the climate in our region was also somewhat drier back then. Evaporation rates, which are greatly influenced by temperature, were also substantially less than they are today. And the net impact of that, these competing processes, was water accumulation in the lowland areas of the Great Basin and the formation of Lake Bonneville. At its peak, Lake Bonneville was about 980 feet deep. You would be underwater right at this location right now if you were here 18,000 years ago. And Lake Bonneville had a surface area of almost 20,000 square miles, making it roughly the size of Lake Michigan. Shortly after the last glacial maximum, Lake Bonneville filled to capacity and began overflowing to Red Rock Pass in Idaho. The outflow from that lake quickly eroded the unconsolidated material near the pass and unleashed a torrent of water, which flowed down the Marsh River Valley to the Snake River. The Bonneville Flood, as it is known, is the second largest flood in geologic history, and it released almost 1,200 cubic miles of water within a period of weeks or months. And it permanently drained more than 350 feet from Lake Bonneville. As the climate has warmed, at the end of the last ice age, the evaporation rates increased. And over time, Lake Bonneville gradually receded, with Great Salt Lake being the largest remnant. As the water evaporated, the lake transformed from a freshwater ecosystem to a saline ecosystem. For thousands of years, Great Salt Lake has waxed and waned in response to annual and decadal precipitation patterns. As a terminal basin lake with no outlet to the ocean, its elevation is controlled by the relative inflow and outflow of the lake. The inflow is a combination of the direct precipitation and the stream flow that comes into the lake, as well as a little bit of groundwater that comes in. The outflow is dominated by evaporation. In the modern age, their anthropogenic activities, such as mineral extraction, have also created an additional outflow pathway. On an annual timescale, the lake breathes. It rises in the spring with the snowmelt and declines in the summer and fall due to evaporation. On decadal timescales, it equilibrates with the prevailing climatic conditions. When the system is in equilibrium, higher than normal amounts of precipitation will cause the lake to rise, and lower than normal amount of precipitation will cause the lake to shrink. The elevation of the Great Salt Lake has been monitored continuously since 1848, basically showing how important it has been to the pioneers and everybody since. And although the average elevation of the lake has been 4,199 feet above sea level over the last 125 years, it's experienced significant decadal variations. In the 1980s, a series of massive snow years caused the lake to rise, and it reached its contemporary high of 4,210 feet. After the peak in 1987, there's been a clear and sustained downward trend in lake elevation. Measurements from last year indicate that 2022 had the lowest annual elevation in recorded history. The dramatic decrease in lake surface area is evident in these time-lapse images from Google Earth. Quite the dramatic transformation. However, the situation in 2022 was even more dire when the lake elevation dropped to 4,188.8 feet last November. This image shows that Farmington Bay and Bear River Bay and the southeast and northeast quadrants of the lake, respectively, are completely dried up, with the exception of small river channels for the Jordan and the Bear Rivers. The area of the exposed lakebed now exceeds 800 square miles. For comparison purposes, 800 square miles is larger than the island of Maui in Hawaii and is roughly half the size of the smallest state in the nation, Rhode Island. Something is clearly amiss with Great Salt Lake, and no one encapsulates that better than our own Pat Bagley, an award-winning editorial cartoonist for the Salt Lake Tribune. So why is Great Salt Lake shrinking? Well, there are basically three reasons: climate change, drought, and water diversion. As the climate warms, evaporation rates increase, making it more difficult to keep water in the lake. We're also in the midst of the worst megadrought in the last 2,000 years, which has led to paltry snowpacks over most of the last 20 years. Lastly, more than 2 million acre-feet of water per year are depleted from the tributary streams and are used for other purposes. Determining the relative contribution of each of these processes to the declining lake level is a complicated endeavor. However, the Great Salt Lake Strike Team, which is formed at the request of state legislators, brings together experts in public policy, hydrology, water management, climatology, and dust to provide an impartial, data-informed, and solution-oriented support for Utah decision makers. Membership of the Great Salt Lake Strike Team includes myself, other members of faculty from the University of Utah and Utah State University, as well as state government officials from the Department of Natural Resources, the Department of Agriculture and Food, and the Division of Environmental Quality, the Division of Water Resources, the Division of Water Rights, and the Division of Forestry, Fire, and State Lands. The next few slides are taken from the Great Salt Lake Strike Team Policy Assessment Report, which was published in February of 2023. So how much has climate change impacted the Great Salt Lake? Well, if you look at the mean air temperature for northern Utah over the last 125 years, you can see that there's no trend up until the early 1980s. And after that, there's been a clear increase in temperature in the region. And the experts from the strike team have determined that this temperature increase explains about 8 to 11% of the water loss from the Great Salt Lake over the last 40 years. Although there is considerable variability in precipitation in northern Utah, there has been no discernible long-term trend in precipitation until the megadrought that has been the last 20 years. And the Great Salt Lake Strike Team experts have determined that this megadrought explains about 15 to 23% of water loss from Great Salt Lake over that same time period. Water diverted from tributary streams will lead to reductions in the measured stream flow. The Bear, Weber, and Jordan rivers have all experienced decreased stream flow over the last 125 years. The Bear River, which delivers about 50% of water to Great Salt Lake, has seen a decline of nearly 38% over that time period. The Weber River, which delivers about 20% of water to Great Salt Lake, has seen an even more dramatic stream flow decrease during that time period. The Jordan River, which flows through our valley, has only seen a very modest decrease during that same time period. And overall, the experts from the Great Salt Lake Strike Team have determined that natural and human consumptive use explains 67 to 73% of our current water loss from Great Salt Lake. That's a good thing and a bad thing. It means that the problems are not being caused by existential threats that we have no control over. It means that the future of the Great Salt Lake is actually within our power to fix. So what is the water being used for? Well, it's being used for agriculture. 2/3 of the water depletion is being used for agricultural purposes, and more than half of that is used to grow alfalfa and hay. Cities and industry use an additional 18%, and mineral extraction uses another 8%. So the water is being put to good use, but we're just simply using too much of it for the long-term sustainability of the Great Salt Lake. So what are the consequences of the shrinking Great Salt Lake? Well, I'd like to frame it in a series of tipping points of things that can happen as the lake shrinks. And the first of those tipping points was the dust. I started noticing dust coming off the Great Salt Lake all the way back in 2012. The next one was recreation. They pulled the last boats off of Great Salt Lake in 2022, ending a long history of recreation. In terms of industry, industry is struggling right now, the mineral extraction industry, but also ski industry potentially. And if we continue down this path, we risk the ecological collapse and the death of millions of birds along the way. And if we don't do anything and continue business as usual, within 5 years, the lake as we know it could be dead. That's what we face. The Division of Forestry, Fire, and State Lands put together this elevation matrix, which looks at how different levels of the Great Salt Lake have impacts. So they have established an optimum level of range between 4198 and 4205 feet, where the lake seems to be operating at a healthy ecosystem. When the lake gets too high, it causes flooding and other issues. But as the lake continues to shrink, we get into more and more dire consequences. And right now you can see that we are in the most extreme red zone, where we're essentially in unprecedented potential consequences. So why am I here today? I'm here to talk about the dust. I'm an atmospheric scientist. I've been studying dust for 30 years and spent the last 7 years trying to understand dust from the Great Salt Lake. And give you an idea about what we're looking at, here is an image, time-lapse from the University of Utah looking at downtown. The Great Salt Lake is off to the right. And this happens to be a day when we have a cold front coming through, and it picks up dust off the Great Salt Lake and moves it into our city. The state capitol disappears, downtown disappears, visibility is less than a mile, and we're all breathing that dust. This is not something that's intangible. You can see it, you can touch it, you can taste it, and it has the ability to impact everybody along the Wasatch Front. So when is this dust most likely to occur? Well, we know that we have challenges for the air quality in the wintertime, but that's not a time when the dust is prevalent because it's too wet out there. We know we have summertime air quality challenges with ozone and wildfire smoke. That's also a time period of low dust. We generally have really good air quality in the spring and the fall, but that's when the dust is most likely to occur. And if this continues, what will happen is we'll move from seasonal air quality challenges in northern Utah to year-round air quality challenges. So where does that dust go? Well, the larger particles can stay in the atmosphere for a few hours. The smaller ones can stay in the atmosphere for 2 weeks. But the larger particles, a lot of that is deposited on our snowpack. And Dr. Mackenzie Skiles at the University of Utah studies the effect of dust on snow. And here you can see dust layers in the snowpack. It darkens the snow and it accelerates the snowmelt. And what she discovered is that that darkening of the snow can accelerate the snowmelt by several weeks, which makes it more difficult to capture that water and has important implications for the hydrology of the region, which other experts will talk more about. The particles in the atmosphere from the dust also have the potential to impact human health. PM10 and PM2.5 are regulated by the Environmental Protection Agency. PM10 particles, about half of those will get in your lungs. The PM2.5 particles, most of those will end up in your lungs. And science has shown that exposure to the high concentrations of these can lead to a variety of health outcomes, including decreased lung function, asthma, chronic bronchitis, increased irregular heartbeat, heart attacks, strokes, and premature death. The recreation loss is profound. The Great Salt Lake Yacht Club, established in 1877. Antelope Island Marina closed in 2014. That's what it looks like today. Clearly, no boating allowed. $1.3 million was spent by the state on dredging Great Salt Lake Marina in 2017, trying to keep it open, but yet the marina closed in 2022. And most of the brine shrimp harbors were also closed in 2022. The extraction industries need canals in order to bring water to their facilities, and dredging and extending those canals has cost millions of dollars. U.S. Magnesium recently put in a permit to extend their canals, and that was recently denied. And the state has decided to divide the lake in two by raising the berm between the two lakes, cutting off water to the northern arm in a last-ditch effort to try and save the southern part of the lake. But doing so threatens the future of Compass Minerals that relies completely upon the water in the northern arm. The risk to our state, $1.3 billion annually. The water and the lake also impact our ski area. The lake effect snow contributes 5 to 10% of water to the Wasatch Mountains. While that may not sound like a lot, the timing of that snow is crucially important. It tends to be early season snow, which helps to kick off the ski season and reduce costly snowmaking operations. The risk generally is about $2.8 million per inch of snow to the state. And I just want to highlight my graduate student, Thorne Merrill. He's skiing here in this image, but he's also created an absolutely wonderful film that looks at the impact of this shrinking Great Salt Lake from a skier's perspective. And it's my understanding that that will be shown at some point during the conference as well. Other impacts to industry, the brine shrimp industry is completely dependent upon the Great Salt Lake. They harvest the brine shrimp cysts, and they use those for fish and shrimp hatcheries around the world. Great Salt Lake produces almost half of the world's supply. The optimum salinity for these brine shrimp is between 12 and 16%, and last year, the Great Salt Lake reached 19%, which put the brine shrimp under great stress. The brine shrimp are half of the base of the food chain for Great Salt Lake. The other half is the brine flies. Now, most people don't really know what brine flies are, but here's a video that'll hopefully give you a better idea. They don't bite, they just swarm, and they're an absolutely wonderful food source for millions of birds that visit Great Salt Lake. There are so many of them that the birds literally just run through the clouds of brine flies with their mouths open, and they can't miss. Until this last year, when the brine flies went missing. For the first time in my time out at the Great Salt Lake, I was out there alone without brine flies and without the birds that feed upon them. And once again, Pat Bagley encapsulates what's going on with the brine flies missing. So what's at risk? It's nothing short of the fundamental entire loss of the ecosystem. And I put together this little video montage to show you where we're at today and where we could be in as little as 5 years. Quite the sobering thought at what could be lost. So let's get back to my area of expertise, and that has to do with dust. So here's an example of a dust storm that is being created on the Great Salt Lake due to thunderstorm outflow. That's one way that we get dust off the lake. But yet we also have cold fronts that can bring that dust into our valley. And here you can see that wall of dust as it approaches the city. So as a scientist, I try and answer important questions. And some of the important questions that I've spent the last few years working on is trying to identify where the dust hotspots are in the Great Salt Lake. Are there potentially harmful heavy metals out there? And how do fluctuations in the lake level affect dust production? And most of the research that I'm reporting on now was completed between 2016 and 2018. So what did I do? Well, I divided the lake bed up into grids and actually went out there with my bicycle and collected soil samples. I brought that soil back to the lab and dried it and sieved it and resuspended it in a chamber so that I could pull out the particles that actually end up in your lungs. And then we did chemical analysis on those to determine what that dust was made out of. I did it all by bicycle. And you might think, why would you do that? Well, if you look on the right, you can see some ATV tracks. And in the middle of those, you can see the tracks from the bicycle. Much less damage to the playa. And it's low impact, low cost. And theoretically, you won't get stuck. But, you know, everybody has a bad day now and then. Poor life choice, I think, is the way it goes. So what did I do? I did something absolutely crazy. I visited all 800 square miles of the Great Salt Lake over a 2-year period. I'm literally the only person on the planet who can say that they visited all of the exposed lake bed. It took me 26 months. I went over 145 trips. I collected more than 5,000 soil samples. And I figured you do it once, you do it right, and then you never, ever do it again. Why not use an ATV? Well, here's why. In the Utah Test and Training Range, they wouldn't let me ride my bicycle because they were worried about unexploded ordnance. I like my legs. So I went with the military folks, and they insisted we go by ATV. Not a good idea. It was great sampling for the first hour and a half, and then we got stuck. We spent 8 hours digging. We eventually got 3 ATVs stuck, and we eventually got them out. But the damage we did to the playa was insane. Give you a flavor for what it's actually like.
You shouldn't be able to ride a bicycle across Utah's Great Salt Lake and not get wet. But that's unfortunately what University of Utah scientist Kevin Perry can do as he studies the lake's dried out bottom, the water having dropped to its lowest level in recorded history in July, exposing 800 square miles of lake bed, an area larger than the Hawaiian island of Maui.
And this exposed lake bed, when the wind is strong and the lake bed is dry, it lifts dust off of this lake bed and pushes it into the surrounding communities.
And that is a big problem. The dust clouds are laced with calcium, sulfur, and arsenic, a naturally occurring element linked to cancer and birth defects.
So what did we find? Well, one of the things that we found is that not all parts of the lake are equally able to be dust sources. If you've ever been to the beach, you grab a handful of sand, you throw it up in the air, what happens? It comes right back down. What you need is small particles, silt and clay, in order to be dust sources. And that silt and clay is delivered primarily through the rivers, the Bear, the Weber, and the Jordan River. And you can see here the red areas are the areas that have the highest proportions of silt and clay. And these are the areas that are most likely to have the ability to be dust sources. And that's primarily in Farmington Bay, in Bear River Bay, and the extreme northwestern part of the lake. So when I was out there doing my research, I was looking at how much vegetation coverage was on the lake bed and what the surface crust actually looked like. Surface crust is a very effective way to minimize the emission of dust from the surface. And it doesn't take much. Even a shallow crust that's only a few millimeters thick is enough to prevent the area from blowing away. So where is the Great Salt Lake vegetation? Whoops. Great Salt Lake vegetation, if you look at the northern part of the lake, it's just too salty for most vegetation, so there's not much up there. On the southern part of the lake, the vegetation is most effectively growing at the areas where there's those small particles, the silt and clay. And so we have vegetation that is encroaching on the lake in the Bear River Bay and the Farmington Bay, and this is beyond the Phragmites. I never went to the Phragmites. It's impossible to travel through there. A lot of this is pickleweed, but there are bushes and other types of things that are going on out there. So about 15% of the lake bed is protected by this vegetation. And 67% of the lakebed is protected by a shallow crust. Another 4% is protected by a moderate crust, and about 1.5% of the lake is a thick crust. So you put all that together, and basically about 3/4 of the lake is protected currently by a crust. And that leaves us with about 26% of the lake as a potential hotspot. But just because you have no crust or an eroding crust doesn't mean that it's a hotspot. You still have to have small particles. And when you have a superposition of basically no vegetation, small particles, and no crust or erodible shallow crust, that's where you get your dust hotspots. And my best estimation is that only about 9% of Great Salt Lake lakebed is currently acting as a dust source as of 2018 when I finished my survey. So what does a dust hotspot look like? You know it when you see it, right? Well, here's an example. We had a crust that was out there, and that crust started to break down, and then it exposed the area underneath, and the wind scoured it. And now you have this depression out on the lakebed where the wind has removed the silt and clay and brought it to the atmosphere. That's how incredibly thin the crust was in this region. It's just barely enough there. And as it started to break down, it turned it into an area with significant wind erosion. And over time, these dust hotspots grow in size, and sometimes they merge into a dust hotspot area. Luckily, we don't have many of these yet, but the longer the lakebed is exposed, the larger these dust hotspots will grow, and they will start to merge, and that 9% will inch up from up to about 24% theoretically. So where are these dust hotspots located? Well, primarily in Farmington Bay and Bear River Bay, with other areas in the extreme northwest, and then over near the Superfund site over on the west side of the lake as well. So you say, okay, well, where does this dust blow? Well, it really depends upon the prevailing winds. Before the cold fronts come, we have strong winds from the south, which will push this dust north. And then after the cold fronts, the winds will ship around to the west, northwest, or north, pushing that dust into the surrounding communities. And basically what happens is everybody along the Wasatch Front is downwind from the lake at some point. So is there anything in the lake bed dust that we might need to be worried about? Well, generally speaking, soil is composed of silicon, aluminum, calcium, sodium, potassium, magnesium, and titanium. Those are the normal soil elements. And the soil in Great Salt Lake has a lot of those elements in it, but it's enriched in the evaporite minerals, the salts, calcium, magnesium, sulfur, strontium, chlorine, lithium, and boron. So it's not like it's Bonneville salt flats where you go out there and it's just a white expanse everywhere. It's basically sandy soil with a lot of salt crystals in it. And in order to determine whether or not it's harmful, basically looking at the Environmental Protection Agency for guidance. And they establish regional screening levels to try and limit the risk for cancers to less than 1 in a million. And the regional screening level is basically the dose times the toxicity. And what they try and do is figure out what the toxicity of the elements are, and then figure out what's the maximum dose that you could achieve to minimize your cancer risk. And if the concentrations are less than the regional screening levels, then it's considered safe. If it's greater than the regional screening levels, then it's potentially unsafe. And you have to then go back and do direct measurements to find out what people are actually being exposed to. So what I found was, this is the arsenic concentrations. The green and the red lines are the regional screening levels for residential and industrial exposure. And every single measurement that I took of arsenic was more than a factor of 10 greater than recommended by the EPA for long-term exposure. That got my attention. And here's a spatial distribution of arsenic across the entire Great Salt Lake. And arsenic is a carcinogen. It can lead to lung cancer, skin cancer, bladder cancer, cardiovascular disease, and diabetes. And it's ubiquitous on the soil of the Great Salt Lake. So is this a real problem, like the New York Times articles scared the heck out of everybody? Or is it something that we need to learn more about? Well, the current health risks due to exposure for arsenic are actually uncertain. We have to know the dose, and we don't currently know the concentration or the frequency that people are exposed. And worse yet, we don't know what fraction of that arsenic is actually bioavailable for people. So this is an active area of ongoing research that we need to continue. But people are always asking me, well, is the arsenic from the mines, or is it industry, or is it naturally occurring? Well, if you have a point source of pollution, then it'll likely be concentrated in a certain area. And there are elements that have high concentrations in certain areas on the lakebed. And these include copper, sulfur, silver, phosphorus, chlorine, molybdenum, zirconium, and lead. All have clear industrial signatures on the lakebed. But arsenic, on the other hand, is one of the more uniformly distributed elements across the entire lakebed. And that doesn't mean that there's not contribution from industry, but it means that its concentrations are dominated by natural deposition over a long period of time. But arsenic wasn't the only heavy metal that exceeded the regional screening levels, but it's the one that was more than an order of magnitude greater. Other ones included lanthanum, lithium, zirconium, cobalt, manganese, and copper. So there are threats out there that we need to have a much better understanding of. And to summarize the potential health impacts, I'm much more concerned about the dust plumes that are visible, that are coming off the lake, that raise the PM10 and the PM2.5 concentrations to unhealthy levels at times. But there is a potential for chronic health risks due to exposure due to some of these heavy metals that we need to understand better. And ultimately, everyone, all residents in northern Utah are likely to be exposed by dust at some point. Once again, Bagley does it. Unfortunately, I've had lots of people call me up after that New York Times article saying, should I move out of Utah? The answer is no. It's a wonderful place to live. And we can protect ourselves, and we have a collective will that will allow us to hopefully fix this problem. So lastly, how do fluctuating lake levels affect dust production? Well, it turns out that the U.S. Geological Survey and the Division of Forestry, Fire, and State Lands flew an airplane over the Great Salt Lake back in 2016 and used a laser beam pointed down at the lakebed in order to determine the elevation of every spot on the lakebed every meter. And I combined that with the location of all of those dust hotspots that you've seen. And we now know the elevation of every single dust hotspot. So you can basically create a model that will tell you what the lake level needs to be to cover up those dust hotspots. And for Farmington Bay, it was quite simplistic. For every increase, so what we have here on the x-axis is the lake elevation. On the y-axis, we have the fraction of the dust hotspots that are covered up by water at that elevation. So if you look at the long-term elevation of the lake for the last 150 years at 4199, that would actually, if the lake were back up at 4199, it would cover up 60% of the dust hotspots that I found in my survey in Farmington Bay. And so it's a very linear relationship. And for Farmington Bay, it was a 13.8% decrease in the number of dust hotspots for every foot gain that you get in the lake. But you'll notice that when I did my survey, the lake was about 4195. In the last 5 years, the lake has fallen an additional 4 feet. And I haven't fully surveyed the lake bed, but this linear trend allows me to extrapolate. I usually don't like to extrapolate, but I haven't finished the research yet. And the extrapolation is that in the last 4 to 5 years, the number of dust hotspots has increased by 40%, which now changes the equation quite a bit. If you want to mitigate 50% of the dust hotspots, you have to get to 4198. If you want to get to 80% mitigation, you have to get all the way up to 4202. And once again, Bagley says it great. We have a wonderful snowpack this year. Are we solved? Is the problem solved? No, it's not. We're miles and miles away from where we need to be for dust suppression. And those tipping points, the dust was the first ecological problem to occur, and it'll be the last to be solved by putting water back in the lake. And I want to acknowledge the Great Salt Lake Strike Team that did much of the research that was presented here in the first part of the talk. Funding sources, the Department of Natural Resources, the Utah Division of Facilities Construction and Management, the National Science Foundation, and support from the Wilkes Center for Climate Science and Policy as well. Thank you very much. I'll defer to you.
Why don't you take a couple questions from the audience?
Okay.
We don't have a slide out here.
Okay. So I'm available for a couple of questions. I'm told I have a couple of minutes. Yes?
Thanks for all your hard work and for the presentation today. Are you aware of any studies into the heavy metal concentrations and other potential dust sources, such as severe lake bed, the West Desert, or the entire Great Basin Desert?
Yeah. So
and how do how do you tell the the source of dust reaching the Salt Lake Valley from those potential sources?
Yeah, so two questions. First is, are there heavy metals in other lake beds in the Intermountain West? The short answer to that is yes. Owens Lake had high concentrations of arsenic, as do many of the other lake beds that I visited in the region. And then, how do we determine the source of the dust? Well, what we're working on is trying to establish chemical fingerprints that establish one type of playa from another. So Greg Carling at Brigham Young University has been working very hard on that, and looking at not only just the elemental ratios, but looking at the strontium isotopes is a way to distinguish. And then we're also starting to, as part of this Dust Squared research project that I'm a member of, looking at whether or not biological components of the dust can be used to fingerprint as well. So what I'd like to say is that the Great Salt Lake is not the biggest dust source in Utah. There are other bigger dust sources. This is the one that just happens to be on our doorstep and is, as a result, the one that we're most concerned about from a human health perspective. Yes?
Are you aware of, kind of mitigation solutions proposed?
So the question is, am I aware of any mitigation solutions? So Owens Dry Lake Bed in Los Angeles, they spent $2.5 billion trying to mitigate the dust without putting water back in the lake. And what they determined is that after $2.5 billion, the most effective way to reduce the dust is to put water back in the lake. Great Salt Lake is 12 to 15 times bigger than Owens Dry Lake, and mitigation would be at least an order of magnitude larger for that. And so I think the prudent thing from a fiscal perspective is that saving the Great Salt Lake itself will be the most cost-effective way to do dust mitigation.
Do we know at what level of the lake the ideal salinity would return? And will the brine flies come back, or is there a time in which if we don't get the lake up, they won't come back?
So that's a little out of my expertise, and so I'm going to defer to some of the later speakers. It's my understanding that there is some resilience in the system, but it's not a threshold that we want to cross and flirt with to come back from. Because in the interim, when the brine flies are gone, the birds that rely upon those will die. And recovery of those populations may be even more problematic.
Did your bicycle survive?
Did my bicycle survive? The first bicycle I had lasted 750 miles until it rusted through. It was metal. I called it the tank. After that, I invested in a carbon fiber bicycle, and it has done quite well, sort of thing.
Kevin, you've got a question on Slido. It's from someone who lives in Cache Valley in the Bear River watershed, asking if the dust will travel up there, and how far does the dust travel?
Yeah, so I mentioned that the larger dust particles will stay in the atmosphere for a few hours. So if the wind is blowing at 20 or 30 miles an hour, that kind of gives you a range of 100 to 150 miles for those larger particles. Those smaller particles will stay in the atmosphere until it rains, which is an average of 2 weeks. And so the dust that's coming off the Great Salt Lake in 2 weeks can be transported all the way to Europe, all the way to China. And we've seen that the intercontinental transport of dust is something that we see every year. In the summertime, we have African dust, which travels across the Atlantic and into the eastern United States. Here in the western US, we see Asian dust that's being transported across the Pacific. The dust from our little lake bed pales in comparison to those dust sources, but theoretically, that dust will stay in the atmosphere for a long time.
Thank you very much.